There's really no situation like but if you're really close to people, then you can be like, as you view your siblings, you can be like, you watch this.
Wait. I love them.
Those are beautiful. That was a beautiful one. That's a struggle. Tessa, like a teacher. That's a year ago.
About the
You can look up.
All right, great. Okay, apologies for 2 blue packets in a row. I meant to mark the gold box on the copy sheet and forgot, so sorry that there are 2 blue ones. The homework is the blue packet. It's the same pattern we've been doing. Find the example in the packet. I think it's on the first page. It says extra example 2E. Okay. So like all FRQs, they give you information, and then they give you a question. I can't quite remember if I've shown you this yet or not, so let's do it now. Borrow Allison's notebook real quick. When you get an FRQ on the actual AP test, it's in a booklet. And it will look like this. Okay, this is the format, a booklet. And the FRQ, the information is given here at the top. And then it will have question A, B, C, and D typically. And whatever's written here is considered one FRQ. So if you do some work here that you now need over here, you don't need to repeat it, you don't need to rewrite it, it's just one big problem. Everyone understand? Okay. So, thank you. They tell us that the rate at which people enter an amusement park is given by this function. Keyword is rate. So this is the middle column on Danica's chart. They're giving us a rate. The rate at which people come into the park. Then they say the rate at which people leave the park is given by this formula. Okay, having done many years of AP problems, this is really common to describe an amount of something. People on the seat on the roof. To describe an amount of something and to have an in rate and an out rate. So look at me. So here's the stop. It's the number of people in the park. There's a rate at which people come in and a rate at which people leave. That's a really common AP scenario. You have an in rate and an out rate. So get used to it, be comfortable with it. It's really common. In rate, out rate. They tell us that both are measured in people per hour. You get points for units, so we want to pay attention to that. T is measured in hours after midnight. That's common for story problems. So you don't have to worry about doing some sort of translation. We're going to go from 9 to 23, which is equivalent to going from 9 in the morning until 11 p.m. But you don't have to worry about the AM, PM, you just numbers, 9, 9, 10, 11, 12. Question says, how many people have entered the park by 5 p.m.? And then there's a stopping point. So I just stop right there and don't keep going. Okay, you must read slow and careful. How many people have entered the park? So they don't care anything about how many left, just how many entered. Okay, the fundamental theorem says, if I integrate the rate at which people are entering the park, let's write that down. So write on your paper the integral E of t dt. And let's pay attention to the units here. Notice. The units of E of t are people per hour. dt means difference in time. So the units of dt are just hours. So you're going to say it out loud here in a second. You take people per hour multiplied by hour. What are the units? People. So the fundamental theorem says if you integrate the rate at which people are entering the park, the integral will calculate how many entered the park. So that's the fundamental theorem. So we want to integrate from time 9 until 9 until 17. So do that integral on your calculator. Go. Stop me if you need help with anything.
Weird.
So the next, you stop there, but it does say round your answer to the nearest whole number. So no worries, so we're okay to just go 6,000 with one. And then, as I mentioned to Rachel, if you keep reading, it says round your answer to the nearest whole number. So if you perform an integral, you must write the integral. That's required. So raise your hand if you have this written on your paper. 2 points, and we need help.
Why do you think the integral of this?
So whenever we have a situation, see if this helps, Hayden. Let's do a really simple comparison. If I knew that 10 people per hour were entering the park, and I knew that 10 people per hour, just really simple example, 10 people per hour enter the park, and they do that over a 5-hour period. How many people would have entered the park during those 5 hours? One more time. So if I know, again, this is a really simple example. If I know that there are 10 people per hour entering the park, we'll ask the whole class. 10 people per hour entering the park, and that's just a steady flow. 10 people per hour. And they enter at this rate for a total of 5 hours. Raise your hand if you know how many would have entered the park during the 5 hours. Elijah? How many knew it? 2 points. Okay, that computation is done by multiplying. The hours divide out, and you end up with 50 people. Okay? In this situation, it's actually very, very similar. The difference is that if you look at the calculator, the blue is the rate at which people are entering the park. So the rate isn't steady at 10 people per hour. It's different. It's just constantly changing. So instead of just multiplying like we did here, 10 people per hour times 5 hours, what we do instead is we take that rate, E of t, and we still multiply it by time, but we do it by a really short amount of time. Then we do it again and again and again and again for this entire time period, and we add all that up, and it does the same type of computation. It computes how many people in total entered the park. I don't know if that helped or not.
Yeah, kind of.
Kind of. We'll keep going for a minute. So that's what the fundamental theorem does. Is you take a rate, like think of it this way. If the rate is 10 people per hour, but the rate only remains 10 people per hour for 1 hour, then you take 10 people per hour times 1 hour. Then you go to the next hour and find the next rate. Multiply those two together. Then you go to the next hour, find the next rate, multiply those two together. Then the S means we add them up. So when we're integrating, that's essentially what we're doing. 2 points. Anybody else? Cool. Please memorize. The fundamental theorem says that if you integrate the rate of anything, like in this case, the rate at which people are entering the park, that integral computes how many entered the park during the time period of the integral. It's true for any rate. If you have, if I pour water from this bottle into some tub, and the rate at which the water flows varies, if I integrate the rate at which water is flowing from this bottle over some time period, I will calculate how much water flowed from the bottle. So it's kind of a rhyme, which helps me. You integrate a rate. If you integrate a rate, you're going to find out how much. So whenever you integrate a rate, you always find out how much. Please.
So if you integrated acceleration, you could get velocity.
You don't get the velocity per se, but what you find out is if I integrate, like if you have a situation where the acceleration of an object is varying over time, and it works even if the acceleration is constant, it still works. If I integrate that acceleration over, say, time 0 to time 5, the integral will calculate in total how much did the velocity change during that time period. That's what the integral will calculate. If I integrate velocity over time, I calculate how much in total does the position change during that time. In this problem, if I integrate the rate at which people are entering the park, I find out over time how many people entered the park. If I integrate the rate at which people are leaving the park, I find out over that time period how many people left the park. And what reminds me, Zach, is this little check right here on the units. I'm going to, when I integrate, take people per hour, multiplied by hours, result is a number of people. If you're doing acceleration, look. The units of acceleration would be something like meters per second squared. The units of dt are just seconds. So when you multiply, you end up with a number of meters per second, the change in the velocity. Perfect. 2 points for Zach. Anybody else? That's the fundamental theorem. So, good to hear. Okay, it says the price of admission is $15. How many dollars rounded to the nearest whole number are collected between 9 a.m. and 5 p.m.? That's not a calculus question. That's just kind of a common sense math question. Raise your hand if you know how to calculate that. Don't overthink it. Just hands up. Who knows how to do the next part of the problem? Let's go, Grant.
You just multiply 15 by the amount of people that entered.
Perfect. So they're just asking you in a kind of common sense way, just figure out the total amount. So how many knew it? 2 points. So just do that quick. Since that's just a multiplication, you don't have to show that work if you don't want to. You can just write down a dollar amount.
Do we need to multiply by the whole number rounded or by the decimal?
Outstanding question. 2 points. Because they said round this answer to a whole number, then we're going to take this times the 15. It's perfect. What's the result?
90,060.
Like that? Perfect. Questions, anyone? Next one. Okay, so go to extra example F, please. I think you know how to do this one based on our discussion a moment ago, so do F. Stop me if you have a question. Go. Always remember that if you calculate an integral, you need to write down the integral. That's part of the requirement. So, what's the result? Isaac?
2,279 people.
Okay, who has that written on their paper? 2 points. Okay. Questions about anything? Cool. Extra example G. It says find the rate rounded to the nearest, so extra example G. Find the rate rounded to the nearest whole number at which the total number in the total number of people in the park is changing. Okay, so it's a common AP question once again. Borrow the water bottle. Okay, in the future you're going to see a question that says there's a tank of water. There's a rate at which water comes into the tank. There's a rate at which water leaves the tank. This problem is really identical. Instead of talking about water in a tank, it's people in a park. There's a rate coming in, there's a rate going out. I've never seen a problem where they had 3 rates, but I suppose they could do that. But I've not seen it. I don't know how you'd quite describe that. But anyway, rate in, rate out. Okay, those 2 rates control whether the number of people in the park is going up or the number in the park is going down. Simple. If the in rate is greater than the out rate, the number of people in the park goes up. If the out rate is bigger than the in rate, the number of people in the park goes down. Please.
So you just find the difference between the 2 equations.
Perfect. So on your paper, you have to write that out. So you just say, let's see, E of 14, and we compare that to L of 14. So on your calculator, you find E of 14. So somebody tell me what E of 14 is.
780.
And they do want us to round to the nearest whole number. I wouldn't round early, though. You only round the final result. So is it 780 exactly, or is it?
Yeah.
Okay, so 780 exactly. So 780 people per hour are entering the park. We subtract from that, 2 points for Sarah. What's the L of 14? Go, Elijah.
290.882.
290.882. Therefore, the result, so this equals this, which equals 2 points for Elijah. Someone else help me. What is it, Aiden? Oh, just my bad. Somebody else. 489.118, and this time we do want to round. So this would be find the rate. So this is people per hour. So the number in the park at hour 14 is going up by a rate of 489 people per hour. Please,
So
Michelle.
if it was negative, it would mean that so many people are leaving.
Perfect, perfect. What's happening all day long is there are people coming in and there are people going out, and they're just always comparing the difference, right? So if this number turns out to be negative, then we're assured that less are coming in than are going out. It's perfect. 2 points. Anyone else? Next one. So go to extra example H. It says, is the number of people in the park increasing or decreasing at time equal 14? And we've already talked about that. We just need to write down the reason. So we just say, since, it's exactly what Mikkel just said, E of 14 is greater than L of 14, the number of people in the park is increasing.
Yeah.
Please.
Is there like a certain way to write the reasons for your answer? Is there like a certain steps that we should follow as writing that?
It kind of varies from problem to problem, but we do enough practice where we kind of see typically the type of things they ask that you should get accustomed to, I would just say, an acceptable way to write it. So this is perfect. They don't expect anything more. Just saying that since E of 14 is greater than L of 14, therefore the number of people in the park is increasing.
Would you say something as little as increasing because U14 is less greater than L14? Or is that too?
Let me just check it. Is the number of people in the park increasing or decreasing? So, no, mine is a good question. So, say again what you would say.
Increasing because U14 is greater than L14?
Yeah, that would be fine. Because the question's asking, is the number increasing? You say yes because, and you say increasing because of that. So that would be fine. Did that answer your question? Okay. 2 for Maya. Anybody else? Let's move along. So next one. So extra example I. It says, suppose 300 people were given the special privilege of entering the park prior to the park's official opening at 9 a.m. Write an expression for the total number of people in the park at time t. So I write down n of t equals there are already 300 in the park. So they're just there. But then when they open the gates at 9 a.m., there's a rate at which people come in and there's a rate at which people leave. As we talked earlier, if I integrate the rate at which people are entering, I will calculate via the integral how many entered. So I want to integrate starting at 9 o'clock, and I'm trying to figure out how many there are at some unknown time. So I don't integrate to 14, I integrate to just some time, t. And I need to integrate the rate at which they are entering. There's the rhyme again. If you integrate the rate, you find the amount. So that integral is going to compute the number of people who entered the park from 9 until whatever time I specify. But as Mikkel said, during that same time period, there is a number who are leaving the park. So I have to take those away. I'm trying to find out how many are in the park. Questions? Okay, there's one thing we have to change here. It is not mathematically legal to have this symbol be the same as this symbol. So this t and this t can't match. They have to be different. And in an integral, these two symbols, for the types of integrals we work with in our class, these two symbols always match. In the future, you'll get some more complicated things if you go on in math or engineering or whatever. But these two can't be the same letter. It's not legal. The reason why it's not legal to have them be the same is because they have different meanings. This T is a specific time. You specify. I want to find out how many people are in the park at 2 o'clock in the afternoon. So this T becomes 14. And that would match what you would put here. You'd be finding the number at hour 14. So you'd put a 14 here, a 14 here, and a 14 here. But you can't have a T here because that would indicate that you need to put a 14 here. But you don't. This has to stay like that. Because when you integrate, this represents every single value of time from 9 until 14. It's 9, it's 9.1, it's 9.2, it's 9.3, it's 9.4, because that's what happens when we integrate. We take all of those values and multiply it out and then add them up. We need to say that again. Just wait. Okay, so go ahead, Elijah, please.
The T in the NT, is that not applying to the T on the top, or is that?
So these two T's have slightly different meanings. This T is a specific specified time, like 14. This T is really a million different values of time. It's 9, 9.001, 9.002, 9.003, etc. until you get to 14. Because when you perform the integration on your calculator, it literally takes all of those different T values and plugs them into E. So these two T's do have a different meaning. Therefore, we can't have them be the same letter. I'm not sure I answered your question.
Well, so the NT, what does that T apply to? Is that the same T as the T on the top of
Yep.
the integral?
So these two are the same. Because you're going to specify, like, the next question actually says, what would be the total number of people in the park at time 14? And so the next thing we're going to do is take and write n of 14 is equal to 300. The 14 here is exactly the same as the 14 here. So that T changes. But this doesn't become E of 14. Because this T really is going to be every possible value of time between 9 and 14. So this one's really a million different values of T. So totally different meaning than 14. Please, Mikkel.
So can't we just put n of t is equal to n of x and then change the t to x?
So let me just finish writing this, but you've got exactly the right idea. So there's several things we could do. Okay, the orange statement is legal because we don't have any extra variables, so it's fine. The pink statement is wrong because these two have different meanings. They can't have the same symbol. So one way to fix it, I'm not sure if this is what you said or not, but I'll do this first, then you can tell me something else. We can change these variables here to anything we want. As you start looking at more and more scoring guides, you'll see that a common change is to put a U right here. Like that. Now it's legal. The U is still representing time, but it's not the same kind of time as this T, so different symbol. 2 points for Mikhail. Elijah?
Do you have to specify the change of the U for the T?
You do not. They're fine to just make a change. They are looking to make sure, though, you don't have these two variables matching. So, please.
Is that the one that we have to change? We can't change that T.
Another way to have written it would have been like this.
Oh,
sorry.
I mean, you know how there's kind of two T's? Did you have to change that one, or could you have changed the ones at the top of the integral?
The other one, right? Yeah, like I could have done this.
So it doesn't matter which one you change.
Let me finish writing it, then I'll explain. Is that what you meant?
Yeah. like
Yeah,
it's
that's
something like that.
legal. I wouldn't do it that way on this question because the instructions specifically said write an expression for n of t, but I'm quite confident that if you wrote this, you'd get full credit. So this, I think, is a little bit better, but I think they'd still give you full credit for this.
Okay.
I need to make my A's not look quite so much like a 9. That's kind of annoying. 2 for Brennan, really good question. That's what you meant, right, Mikkel?
Yeah.
Awesome. Please, Peyton.
So on the yellow, yellow one, is it okay to change it back to T? Actually change it from T to U?
It is, and they don't really care because now there's no double variable, so it's totally fine to go back to T. They will switch back and forth without any warning. It's just accepted practice. So, 2 points. Anyone else? Please.
So you can really use like any of those options?
2 points for Noah. For this question I, you could not give this. They wouldn't give you credit for that because the question specifically says we need an expression for n of t, the total number at some unknown time, and this is the expression for the number right at hour 14. So you wouldn't want to write this. That wouldn't get you the point, but the other 2 would be fine. Anyone else? Really good questioning. Really good. Okay, the next question in the sequence, the next extra example, simply says go find how many there are at hour 14. So then you just plug it in. So run that through your calculator, make sure it works. And then I do need to round, so let's fix that. So run that through your calculator. Tried to resist the temptation for about 12 steps, and then I couldn't resist it any longer. Questions, anyone? Oh, please, Avery.
So I already have a number stored in my calculator for A. How do I get rid of that?
You don't need to worry about it. Whenever you need to use A again, you just store the new thing in it.
But if you're just using A as like a variable for something else.
Oh, on your calculator, we just always use X as the variable.
Okay.
Yeah. 2 points, anyone else? Next thing. So next one is extra example K. A new situation. So I keep borrowing Maya's water bottle. So I said that we have a tank of water, you have a rate at which water comes in, a rate at which water goes out. We have a number of people in an amusement park, you have an in rate, out rate. This problem is similar again. This time the amount they're talking about is number of gallons of pollution in a lake. But this time, instead of giving an in rate and an out rate, they combined them into a single rate. We could have done that on the last problem, like notice this. On the last problem, we had n of t is the number of people. So number in park. That's an amount. It's a number of people. It's not a rate, it's an amount. And then the rate at which the number of people in the park changes is n prime. And in the previous problem, n prime would have been simply the in rate subtract the out rate. That's the overall rate at which people are entering, the overall rate at which the number in the park is going up and down. And you me to talk more about that?
So that one's like the rate and it's people per hour.
So this is the rate, 2 points for Hadley, and this would be people per hour. Okay, this new problem, what's different is there's still an amount. The amount is P of T. And it's the amount of pollution. So it's an amount, and it's gallons of pollutant in a lake. Okay? Then P prime is the rate. And this time they didn't give two separate rates. They didn't give like a rate at which pollution enters the lake and a rate at which pollution leaves the lake. Just one rate at which the amount of pollution is going to change. So this is the rate, and it would be measured in gallons per hour. I think in this case gallons per day, is that right? Help me.
Yeah.
Gallons per day. So the key thing to notice is sometimes on an FRQ, they give you two rates which you can combine to create a single rate, but other times they just give you the single rate. You can't split it. Anyone want me to talk more about that? Cool. So at time equal 9 is the amount of pollution in the lake decreasing or increasing. So what I did is I graphed P prime of T on my calculator, and I got this picture. See if you can do the same. Go. Oh, please, Elijah.
Question on it.
Oh, thank you. All eyes up here. I forgot about that. Everybody look at me. The question that's on your paper is a bit confusing, so I decided that it would be better not to discuss that at this point. So just rewrite item K. My bad. That happened last period. It didn't turn out very well. It was better to just, let's do this instead. So just change item K. So the description doesn't change at all. All that changes is the K question is a little bit simpler now. So just rewrite K to look like that. 2 points for Elijah. And then get that on your graph, on your calculator. How many have this on their screen? Show me your head. Still trying? Wait another minute. So. Need help, just stop me. Yeah, you just have a slightly different window, so you're okay. There's no problem. That's okay. The window I ended up choosing, I just kind of played with it for a little while until it looked pretty good. But yours looks fine. I ended up with a window, let's see, reload this. 2002B. So I went window 0 to 10, zoom fit, and then I'd probably go change my Y maximum to 0. And then just graph. So how many have this, or at least something pretty similar? Show me. 2 points. Okay. So they want to know at time equal 9, is the amount of pollution in the lake increasing or decreasing? Okay, so you just write on your paper, P prime of 9 is the rate, P prime of 9 is the rate at which the pollutant in the lake is changing at our, or in this case, day 9. So P prime of 9 is the rate at which the pollution level is changing on day 9. So you find that on your calculator. Somebody help me, what's the number?
Negative 0.646.
So negative 0.646, we need to put in units. So that would be gallons per day. 2 points for Zach. So this tells you that the amount of pollution in the lake is going down by 0.6 gallons per day. The amount of pollution in the lake is going down by 0.6 gallons per day. So that's what you write.
Wait, where did the 646 come from?
So they took this equation. So on my calculator, I can do it 2 ways. One, I could just do trace. That's the wrong button. Trace, and go to day 9, and just read the value. Negative 0.646. Is that okay?
Yeah.
2 points for Rachel. So is the amount of pollution increasing or decreasing? Decreasing. They don't say I have to justify, so you don't have to justify. You do need to show this number, though. Otherwise, it's just a guess. They won't give you credit for guessing. So, question? Cool. Next one. How much pollutant is in the lake at time equal 9? I think we've discussed enough that I'm hoping you can do that on your own without help from me. So go, you can work with each other if you need to. Stop me if you have a question. Oh yeah, you're. Oh. It's a little hard to do. So work problem L, please.
Did you get negative 9? See, but isn't that integral just giving us a number? So why are we asking value?
You can't have negative.
And it's also perfect for standpoint if you're writing what they want to see.
I'm going to ask him how we know.
Ow. Should be Wait, I've got to minus 13 minus 0.
That's a big Emma.
Yeah, and then the next question is like, is the link safe for taking time? And
I know, it's cheap. That's why. So it gives you a negative.
is this thing where you put a variable?
find what the rate of the actual solution.
That's
Oh, I think
I appreciate it. Very It's just
then you can like rearrange it, solve it. You could P prime
but like, so is it
Hey, eyes on me. Two for Bennett. It's a very good question. Eyes up here. Everybody look. Everybody. Drew, look up for just a second. Allison, look up for a moment. You're good. Okay. When we need to find the total distance traveled by a moving object, we do integrate the absolute value of the velocity. That's total distance. But otherwise, I don't recall ever needing to integrate the absolute value. So that's a pretty unique case. To find total distance traveled, we integrate the absolute value of the velocity. Doesn't mean we won't run into some very creative problem where we need to, but it's not common. This problem, we don't want absolute value because we want the integral to tell us whether the pollution level went up or whether the pollution level went down. So the positive and negative is important. So absolute value throws out all the negative. We don't want that. So I liked what Camry did, and then Brendan was doing the same thing. Camry said, I integrate from time 0 to time, let's write it this way. She's thinking, okay, if I integrate from time 0 to time 9, the rate at which the pollution level is changing, if I integrate the rate, I get an amount. So I integrate the rate, and I find the amount of change in the pollution level. So this integral came out to be negative what, Camry?
9.285.
And that would be just gallons, because this is gallons per day, this is days. When we multiply them, gallons per day multiplied by days just gives me gallons. So we have this as the amount of change in the pollution level. Then Camry said, I need to combine that with the fact that we start with 50 gallons in the lake. That's how much is there. The integral is telling us the change in that amount. So that's going to be the amount of pollution on day 9. And that would be, read it to me, Camry, 40.715. Okay, required elements. You must show an integral. So I showed that we're going to take 50 plus this integral. Camry did it a slightly different way, which was just as valid. She said, I'm just going to find this integral first. So she wrote down the integral. She told the grader the value of the integral. Then she said, okay, 50 plus that. And then she wrote the final result, 40.715. You don't technically have to label because they're only asking for one thing, but Hadley?
Can you also, like, you can take like the fundamental theorem, and you can say that because like when p of 9 minus p of 0 is equal to that integral, and that
Absolutely. No, it's perfect. Does that make sense? Yeah. So Hadley did this. She started with the fundamental theorem, which says if I integrate from 0 to 9, p prime, I'm going to get this. And then by rearranging, I can get what I had here. Perfect. Okay, all eyes on the board for this one. It's really good you brought this up. 2 points. Everybody look. Everybody. Okay, in a story problem, doing like this step, this step, this step feels pretty good, it makes sense, okay? There will be problems in the future that don't have any story associated with them. And doing this is easier. So make sure this makes sense. Because in a story, this flows pretty easily. Without the story, you pretty much have to start here. Okay? So this is important. Start here, rearrange to there. Perfect. Please.
So the interval of a rate, like you were saying, gives you the amount. So like, is it just because it's like 50 in the way the question is? Like that because like how is negative 9.285 an amount or something?
The reason it's an amount is P prime is a rate. And I've got to give you kind of simple numbers, otherwise it's too hard to think about. So if the rate starts out at negative, like say at time 0, the rate is negative 2 gallons per day. Well, you multiply that negative 2 gallons per day by some amount of time. And the multiplication tells you by what amount did the pollution level change in that short amount of time. And then you go to time point 1. So now the rate's negative 1.9 gallons per day. And you multiply that new rate by a short amount of time. And you find out how much did the pollution level change in that tiny amount of time. You do it repeatedly and then add up all those little changes, you get the total change in the pollution level.
So it gives you an amount, but you just have to compare that amount to the starting amount
Right.
of that. Okay.
Right, because we're saying, let's write this down, I think it will be better. It's a really good question, 2 points for Brennan. So what we're saying is, the pollution level is changing by 2 gallons per day initially. And we multiply that by a very short amount of time, like 1/100th of a day. And we find out in that 100th of the day, the level of pollution in the lake went down by 0.02 gallons. That's not how much pollution is in the lake, that's how much the pollution level changed by this amount in that time. Then in the next 100th of a day, the rate is different. It's now 1.9 gallons per day. So we multiply that by 100th of a day, and we get negative 0.019 gallons. So this is how much the pollution level changed in that next little fraction of time. When we integrate, we're doing this series of multiplications, and then we're adding all those results together. That's the big S. So we get a total amount of change. It's a change in an amount.
Okay. So I guess like when you were saying how much, I was thinking like how much, like I have 2 cups of that, but it's not like how much like with a thing. It's how much it changed in between those two.
Perfect.
Okay.
Perfect.
Okay.
The integral always tells you how much something changed.
Not just how much is there. So like the amusement park was telling you how much it changed from the 300 starting people, not how much is just there now.
Correct. That's why you had to have the 300 in addition.
Okay.
Perfect. Anybody else? Awesome. Okay, so next one. M is really simple. It says, is the lake safe at time equal 9? There's a statement up here that says the lake is considered safe when it contains 40 gallons of pollutant. So you just write down at time equal 9, there are 40.715 gallons, so the lake still isn't safe. That's it. Please.
If that number had been 40.415, would you round it down to 40 and it would have been safe?
Because the question doesn't say anything about rounding, I wouldn't round. Good question. Good point. What else? Okay, go in the packet. That's all the extra examples. I want to do one of the assigned problems that's a little bit trickier. So go to number 9. So go forward in the packet until you find question 9. Okay, again, yeah, they come up with, it's really crazy. They must have some sort of like lunch meetings day after day and say, what did we talk about this year on the test? Because they have talked about, since I've been teaching, the first test I gave was 2007, They've had water in a tank, they've had a river, and like the amount of water in the river, so that way it's measured by like how high the water is on the banks of the river. So instead of talking about a tank of water whose level goes up and down, they describe a river whose like distance from like the water goes into the shore. You know what I'm saying?
Yeah.
Like the level of the I can't even talk. The level of the river goes up and down. They've had problems that talked about you go to a grocery store and there's a big pile of potatoes on a table. I kid you not. Like I don't know how in the world they think some grocer's in there going, I think I'll do a little calculus today to figure out, you know, it's stupid. But that's what they have, like potatoes on a table. I've seen bananas on a table, I think. There have been grass clippings in a bin. Like there's some guy has a mowing business and he like mows the lawn and picks up his grass clippings, puts them in a bin. There's been snow on a driveway. Like snow falls, and so there's a rate at which snow is falling, right? And then there's Janet is her name. She's cleaning off the driveway. I don't know why I remember this. Look, it's hilarious, okay? But all you have to do is forget the story, really. Just think, I have an amount, okay? There's an in rate and an out rate. Or in some cases, there's just one rate that combines them. In this problem, mosquitoes on an island, okay? And one rate to describe the rate at which that number of mosquitoes goes up and goes down. So this one doesn't have an in and an out rate, it just has one rate that combines them. Work on this for a minute, and then we'll talk. Go. So working on 9 and 10, really. Work on 9 and 10, and then we'll talk. If you want to ask me something as I walk by, go ahead and ask. If it's too complicated, I'll just tell you to wait, but you can ask. You're welcome. So in this problem, they don't really care what the number of mosquitoes is at time 6. Just want to know, is that number going up or going down? This one's going to be a little bit like what you asked earlier, Drew, about like when we get to 10, it's going to be kind of like the speed. So I started with 1,000, it would have gone down by this amount. That kind of implies, that makes you think that the number of mosquitoes is decreasing, but not necessarily at day 6. Let me show you on the board. Yeah, there you go.
Why?
Yeah, that's, Ellie knew exactly where I was headed.
Why?
I need the graph.
It's just what the value is.
Okay, everybody's on the board. Everybody look up. Okay, the question asks us to figure out on day 6, is the number of mosquitoes increasing or decreasing? On day 6, is the number of mosquitoes increasing or decreasing? Actually, it says show that the number of mosquitoes is increasing. Okay, warning to everybody. So everybody's looking at me. Look up, Drew. Okay. Don't ever answer a question about increasing or decreasing by making a comparison between two values. Like you can't say, well, let's find the number of mosquitoes at time 6, and let's compare that to the number of mosquitoes at time 5. Comparing the two numbers will not guarantee a correct answer. Because if the number of mosquitoes on day 5 is, I'm making up numbers to make this discussion easier. If the number of mosquitoes on day 5 is 1,500, and the number of mosquitoes on day 6 is 1,600, you cannot absolutely confirm that on day 6 the number of mosquitoes is increasing. Who knows why that can't be done? Okay, everybody. So you work out and figure out on day 5 there's 1,500. On day 6 there's 1,600. They won't give you any points if you say, oh, therefore the number of mosquitoes on day 6 is increasing. What's the flaw in that argument? Let's go, Hadley.
Well, so then because it's a rate, the number of mosquitoes on day 5 could be increasing too, and it could be higher than the number of, like the rate that mosquitoes are increasing on day 6.
It's you got the right idea. Just knowing the number on day 5 and comparing to day 6 doesn't guarantee that right here we're still going up. Right here we could actually be going down. Ellie was kind of indicating that. 2 points for those who have their hand raised. So when they say at day 6, is the number going up or down? You just need to look at the rate on day 6. It's Danica's chart. Watch. We have N of T. They don't give me a symbol, so I'm going to invent one. I'm going to say N of T is number of mosquitoes. Therefore, N prime of T is the same thing as R. N prime is the rate at which the mosquitoes are changing. Danica's chart says if N prime is positive, N is increasing. If N prime is negative, N is decreasing. So I need to go find the value of N prime, or the value of R at time equals 6. So using your calculator, Brennan, what's the value?
4.438.
Okay, we'll pay points to the whole room. Raise your hand if you know what units belong here. Everybody who knows, come on. Wait, we got to keep track of units. You get quite a few points on the test for units. So what are the units for? If you just read, it'll tell you. What are the units here? Boston?
Mosquitoes per day.
So how many knew that that was mosquitoes per day? Show me your hands. Just want to see how we're doing. 2 points. Okay.
I didn't know you used mosquitoes.
I don't know that that's legal, but I'm pretty confident the AP test would give it to you. So they're not super picky on spelling or grammar or anything. So, anybody else? Please.
How did you get R6?
So they gave me an equation for R. So I just took my calculator, typed in the equation for R, and then a couple ways I can do it, either from the main screen or the graph. I just find out what's the value of R at time 6, on day 6. I just got typed wrong. I'll come check in a second. Hold on. Is everybody okay? I'll help mine in a minute. Is everybody okay here? Awesome. Next question says, on day 6, is the number of mosquitoes, is N, increasing. We know n is increasing at an increasing rate. That means I need to find out whether this rate itself is going up or down. So I need the derivative. I need the derivative of r. And I need to find that derivative at time equals 6, which means I'm finding r prime of 6. You can do that on your calculator as well. Anybody have that already? What is that, Avery?
Negative 1.913.
913? 3? Raise your hand if you know these units. Come on, hands. What are the units that go here? Rachel?
Could be mosquitoes per day squared.
Nicely done. So mosquitoes per day. You can say day squared, or you can say mosquitoes per day per day. Means the same thing. How many knew this? 2 points. So this tells you the rate at which this rate is changing. So the rate itself is going down. So the number of mosquitoes is going up, but the rate at which the number of mosquitoes goes up is decreasing. It's growing slower and slower.
Why do you think a derivative, and why is it
So the reason I need a derivative, the homework is the blue packet. So the reason I need a derivative is I need to figure out whether this rate itself is increasing or decreasing. So this says, right, I'm going to round to make it easier to talk. This is telling you every day the number of mosquitoes on the island is going to increase by 4. This tells you every day this rate's going to go down by 2. So tomorrow, the rate will only be 2 mosquitoes per day, because the rate of the rate is so n is going up by 4 mosquitoes per day, and the next day it's only going to go up by 2 mosquitoes per day. So the rate of increase is decreasing. So if I want to find out Danicus chart.
You know, so on our test last year, the very, it was one of these, and it was the rate of people getting off the escalator, the rate of people on that space was like,
I mean, it might be difficult.
like people going up the escalator, like the escalator moving down.
Okay, Danicus
It
chart.
was so confusing.
This question wants to know is the number of mosquitoes
60
increasing.
people get off the escalator in an hour, but that's just pushing out 40 people per hour.
So I determined that n prime is positive. Therefore, at day 6, n is increasing. This says, is this rate increasing? Like that. So I've got to go take the derivative of r. Find out whether this is positive or negative.
My question is, do you actually have to put values or do you just use the graph?
Oh, gotcha. They prefer, I don't know if any points to be explained from the graph. I want to change finding the numbers. It's not the graph explanation, it's that. That's just